In this video, we try to design a magnitude comparator. Magnitude comparator is a circuit that compares two numbers, A and B as an example, in order to decide whether A is greater than B, or A is equal to B, or A is less than B. The comparator in this case will be a conventional circuit that has number of inputs depending upon how many bits each of A and B has. So if we assume that each one has 4 bits as an example, A has 4 bits and B has 4 bits, the number of combinations for inputs will be 2 to the power 8 combinations, and it will have 3 outputs, either greater than or equal than or less than. On the other hand, if A has n numbers, n bits, and B has n bits, the truth table will have 2 to the power 2n entries, which is really impractical to design. So we try to do it in a different way, which simplifies our life. We come to the following question: how can we determine if two numbers are equal? Let us look carefully at the two numbers. If we write A as A3, A2, A1, A0, and if we write B as B3, B2, B1, B0 for 4-bit numbers, so each number has 4 bits as an example, and ask ourselves, when will A be equal to B? We find that A is equal to B if and only if A3 is equal to B3, and A2 is equal to B2, and A1 is equal to B1, and A0 is equal to B0. Therefore, to simplify our life, we define a new function. We call it xi, where I is equal to 0, 1, 2, and 3. And we say that AI is equal to BI means xi is true, which means xi equals AI and BI, or AI prime BI prime. In other words, xi is 1 if both AI and BI are ones, or AI and BI are zeros, which is the exclusive NOR, or the equivalence function that we defined several times in the past. Now, with the definition of xi, we can say that A is equal to B is equal to the function x3 and x2 and x1 and x0. In other words, let's look at this. Let us take A equals 1011 and B equals 1011. Of course, here A3 is equal to B3, both ones, and A2 and B2 both zeros, A1 and B1 both ones, and A0, B0 both ones, and we can say A is equal to B. So the equivalence, this equivalence function simplified the circuit for A is equal to B. But how about A less than B and A is more than B as an example? So let us see next how do we A is more than B if we take it as case 1, and then we say, how can we tell if A is more than B? Let us write down A3, A2, A1, A0, and B3, B2, B1, B0. When will A be more than B? If A3 is equal to 1 and B3 is equal to 0, clearly A is more than B, and we don't need to look at the other bits, as a matter of fact. So usually we look at the most significant bit where A and B differ. And if A is equal to 1, B equal to 0, then A more than B. If not, A will be less than B. Of course, if A3 is 1 and B3 is 0, we are done. A is more than B. However, if A3 is equal to B3, we look at A2 and B2 in this case, and if A2 is 1, B2 is 0, then A is more than B, and so forth. So we can write down when A and B have 4 bits each, we can write down the formula as follows: If the difference is in the first digit, we say A3 B3 prime, which means A3 is equal to 1 and B3 is equal to 0, and in this case A is more than B. Otherwise, if A3 is equal to B3, which is X3 is true, either both are ones or both are zeros, we look at A2 B2 prime, which means if this is 0 1 0 0 and 0 0 1 1, this is equal. A3 is equal to B3, but A3 is 1 and B3 is 0, and we don't look at the other bits. We say that A is more than B. And so on for the other digits. They are all the same, and we can conclude the following. The function A is greater than B is equal to A3 B3 prime, which means A3 is 1 and B3 is 0, or X3, which is A3 is equal to B3, and A2 B2 prime, which is A2 is 1 and B2 is 0, or X3 and X2, which means the first two bits of A and B are equal to each other, and A1 B1 prime, or finally X3 and X2 and X1 and A1 A0 B0 prime. So that is the function for A is equal to B, and the same thing exactly for A less than B. We can swap A and B in the above formula to get the Boolean function for. In this case, we repeat all the equations here. A is equal to B equals X3, X2, X1, X0. Easy. A is more than B. We have just derived A3, B3 prime, or X3, A2, B2 prime, etc. And A less than B is equal to A3 prime dot B3, which means A3 is 0 and B3 is 1, or X3, which means A3 is equal to B3, but A2 prime B2, or X3, X2, A1 prime B1, or X3, X2, X1, A0 prime B0. So the beauty of this design is that it can be extended to any number of bits, which means if A and B are 8 bits each, we do it exactly the same, which means A is equal to B equals x7 dot x6 dot x5, etc., etc., and A is more than B equals A7 B7 prime plus x7 A6 B6 prime, etc., etc., and this is easy because the size grows with n square otherwise, where n is the number of bits. The circuit to do this actually is not really very complex. It is a simple circuit. Let us look at it, the circuit. First of all, we draw the circuits for the equivalence function, which is x3. And for x3, that's so easy because we have here A3 and B3. We put inverter for B3, we have B3 prime here, and inverter for A3, A3 prime, and we AND. So this is A3 prime B3, and this one A3 B3 prime, and we put NOR gate, so we have x3. That's the equivalence function. Same thing exactly, we have the circuit for x2 and x1 and x0, and we AND all of these together. So this AND gate, it's ANDing x3 dot x2 dot x1 dot x0 to get A is equal to B. That's easy. Now, the other two circuits, if we look at A is more than B, this is equal to, as we have just mentioned, x3. So that is x3. That's x3 from here. Sorry, A is more than B equals A3 B3 prime, which is A3 B3 prime here. We take it to the OR gate, either A3 1 and B3 0, or x3 and A2 B2 prime. So that's x3 and A2 B2 prime, or x3 and x2. No, it comes here actually. x3 and x2 A1 B1 prime, or x3 x2 x1 B A0 B0 prime. That's A more than B. Same thing exactly for A less than B. That's equal to A3 prime B3 as we see here. So we get it from the other part, A3 prime B3 here, or X3 and A2 prime B2, or X3 X2 A1 prime B1, or X3 X2 X1 A0 prime B0, which we obtain through these AND gates also. So that is the 4-bit magnitude comparator. Again, the beauty of this is that it can be extended actually to any number of variables, any number of bits to A and B, and the circuit is very much the same.